Next up, we have Antoine Bocquier. He is going to be the first speaker of the next session, which is entitled Lunar Missions. We will see it isn't all about lunar missions, but that is the working title. So Antoine Bocquier from ispace Europe is going to talk about the first European rover on its way to the moon. And I don't know if Antoine is in the room. Do we have Antoine Bocquier? It seems we don't have Antoine Bocquier. Aha. A little mini marathon. Hello, hello. Nothing like launch yourself onto the stage, Antoine. Here we go. The clicker is just there.
A bit warm up to come to you. It's my pleasure today to present you the ispace Tenacious rover, first European rover on its way to the moon. As you know, the ispace mission is currently orbiting the moon. This is the second mission from ispace. This picture was taken on the first mission with an incredible eclipse over Australia. And I'm excited to show you a fresh new picture. It's not there. It's OK. It's online. Showing the lander in orbit around the moon. Inside this lander, we have the Tenacious rover that sits on top of the lander. It's a rover we made here in Luxembourg. And this rover is the first European rover ever flown to space. I know it sounds incredible. This is a technology demonstrator that will be demonstrating mobility on the surface of the moon, as well as how a small commercial low-cost platform can achieve meaningful exploration, acquire data on the surface of the moon. We also have a scoop that will collect regolith from our partner Epiroc. That regolith will be sold to NASA. This, using the space resource law from Luxembourg, it will also be a first legal demonstration of a commercial transaction of the moon. Further on, one of our commercial payloads is Moonhouse, an art payload that will be deployed on the surface of the moon and imaged. But let me introduce you a bit more about Tenacious. What is a rover about? This rover is an ultralight concentrate of technology, only 5 kilograms of technology. 5 kilograms, again, very light for the constraints on the moon. This rover consists of a monocoque of carbon fiber, very light, produced here in Luxembourg, by the way. It has a radiator on top with most electronics. Its MLI is also a custom design. Mobility-wise, we have 4 wheels, 4 motors with independent control to drive backward, forward, skid turning, spot turning, arc turning. And we designed the wheels according to some research made in Japan for more than 10 years at Tohoku University. Speeds ranging from 1 centimeter per second to 20 centimeters per second. Pretty fast, but we'll keep it safe. The rover can overcome slopes up to 30 degrees. Pretty steep as well, but we'll keep it safe and easy at the beginning, at least. On top of that, the rover has onboard cameras, front and back. Navigation cameras with a large field of view, HD resolution, and even streaming on the front camera, video streaming. As an operator, it's going to be a huge increase of efficiency when we see the pictures, coming back live as we drive the rover before sending the next command. This is crucial when it comes to such a short duration mission to achieve as much as possible. Then the power is provided by a solar panel to a battery. The rover uses very little amounts of power. we have redundant radios on the rover that will communicate with the lander back to Earth using the European ground network ISTRAC. Then the signal goes to Tokyo, back to Luxembourg, and we will be controlling the rover from Luxembourg. Most components are procured in Europe. Everything has been selected. Some are space-rated components. Some come from the industry with the goal of having a platform that's low cost, and that was produced in a very short time frame. The software was also mostly developed in-house in only 2 years, which is an incredible achievement from the team led by Ramon Castella. So then, what are we going to do on the lunar surface? Upon landing, we will turn on the rover, commission it, verify that every subsystem is nominal before deploying the rover on the lunar surface. That's the critical part, with extendable struts, the deployer, bringing the rover close to the ground and dropping it. It's going to be a small job. After that, we will release the solar panel, as well as the antenna, to achieve stable communications and power generation. That's the crux. From there on, we will go a bit further away from the lander, taking pictures of the lander, of the surroundings, characterizing the environment, deploying the scoop, collecting the regolith, sending it to NASA, deploying the moon house, taking pictures, before going to exploration and science experiment goals in the next phase of the mission. All of this, of course, was made possible thanks to an incredible team and the support of the Luxembourg government, which I would like to acknowledge here. This team is made of individuals from all around the world who joined ispace a couple of years ago. This office has 8 years, and we are located here in Luxembourg, close to the main station. Our mission is simple: be the end-to-end providers of rovers to lunar missions, for lunar missions. We design rovers, we build rovers, we test rovers, we operate rovers. That's as simple. I can tell you it's been quite a ride when it came to this rover that we had to design, build, and test and operate within only 3 years, from kickoff to launch this January. So quite a sprint. And I'd like to tell you a bit more about some of these different steps. For instance, when we built the rover last year, in June 2024, this was done in only 1 month before going to testing. This is in our clean room in Luxembourg, where my colleague Rick here was harnessing the last components, last electronics. On the right is the integration of the payload. It's a video available on YouTube. I recommend to watch. Then, next stage. After building the rovers, we had to test them. Last year, 2024, we had 7 test campaigns all around the world, from mechanical to thermal testing here at Airbus. Amazing team, amazing support. We later on went to Japan for 2 months in order to integrate the rover during the summer on the lander, perform functional test, deployment test, communication test. This was at the JAXA Tsukuba facility, Tsukuba Space Center in Japan. And this year, our focus in 2025 was on field testing. So we've been to a series of locations to get operational feedback, to train the operators, know a bit more about the system. From lunar yards here in Luxembourg, at our office, at the university, at the quarry, at the border, up to the slopes of the Teide volcano at 2,000, 3,000 meters in the Canary Islands, and at this incredible facility in Cologne, at the European Astronaut Center, the Lunar facility, brand new one. Each of these sites brought a series of lessons learned, of highlights and features that we could test. For instance, in Tenerife, we were able to test long-range driving, and for the operators to understand how to follow a traverse from orbital maps through the vision of the rover cameras, which is basically a baby vision of the world, being solo. And that was quite challenging, actually. So how can we use the sun to orient ourselves? How can we use boulders, avoid boulders, use features? How can we test the mobility, the range of the radios? Lots of lessons learned to improve our ConOps and also get the experience for the operators. We then went to Cologne, to the Lunar facility, amazing facility managed by ESA and DLR, where a lot of features are simulated, boulders, craters, rims, and on top, the illumination is pretty realistic. So for us, it was very challenging to see how can we drive in shadows, how can we drive in loose terrain. And that is where we did a lot of testing on the mobility, for instance. Here are different tests with slopes testing, loose terrain, deployment of the moon house, one of our payloads. And on top of that, we had payload testing with a scoop as well. Quite a nice picture where you can see both payloads with a house being deployed and imaged before we moved on to scooping. Scooping is crucial in this mission, not only for the contract we have with NASA, but also to leverage this excavation capability to start manipulating material on the moon, to start performing science experiments. How can we get some insights? How can we study the angle of repose of the regolith, trench, compact, and get the most out of it? Last but not least, operating will be the crux. And I'm proud here to present you the operators, the 3 teams plus a backup, that will be operating from Luxembourg. These individuals come from very different disciplines. They have been trained for more than a year. And as a pilot operator, I'm very proud and excited to work with them in the next weeks. On top, we have a series of tools developed in-house in order to perform mission analysis, update live traverses during the mission, based on topography and rover features. Overall, this moon adventure is all but a human one. And I would like to acknowledge all the people on board that journey, from our colleagues in Europe, in Japan, to our partners, our customers. Thank you to LSA, thank you to Airbus, Tubitac, JAXA, all these people who've been showing their passion and dedication to make it happen. Last but not least, congratulations as well to Firefly and Intuitive Machines for the achievements. Very impressive and very inspiring for all of us. So I can only invite you to join us on the 5th of June in the evening. Perfect time to relax, sit back, and enjoy. Thank you very much.
Thank you, Antoine. Thank you very much indeed. Thank you. I don't know if there are any questions for you from the audience. I think we're going to move on. Thank you, Antoine. Thank you. So next up we have Daynan Crull from Karman Plus. He is the mission architect and the co-founder, and he is not going to talk about lunar missions, but a little bit beyond.
Thank you, Lisa. Yes, I'm Daynan Crull, and I attended first in 2022 Space Resources Week, met some incredible people, and made some connections that I hope last a lifetime. So yeah, we're going to talk about asteroids. Who are we? Well, we're a US-based company, and we have a mission to mine near-Earth asteroids to provide abundant, sustainable energy and resources for the space economy. You can read more about what we're doing online. We try to be frequent and detailed in our updates. We really do believe transparency is the best way for us to move forward here, and encourage you to take a look at that. What I will say here, just in terms of our vision, is that my co-founder and I really think about resources as being such a vital part of our civilization. I mean, they've demarcated our history in terms of Stone Age, Bronze Age, Iron Age, the Silicon Age. We think the Regolith Age has the capability of being so transformative. You know, we're excavating things from our Earth's crust that prevailing theory is came here via asteroid in the early bombardment phase. So it's long been the part of science fiction, and now less fiction perhaps, that asteroids are the ultimate source of a lot of these resources in abundance and sustainability. This is a generational problem, we believe. I used to work in climate change, and I remember as recently as 15 years ago, people telling me, and from all political sides of the spectrum, why are you working on this now? There are more urgent problems. We can't have that mentality. So one of the things we need to think about with generational problems is how do we make the steps to get to where we need to go? Can you imagine a scenario where we have moved mining off Earth and we're now getting resources and producing products from them in space? We have space-based solar power. This is a concept we've designed, taking a look at how you're continuously collecting sunlight, transmitting it into microwave energy and transferring that to Earth. That technology is being looked at here in Europe and the US and Japan, but There are significant roadblocks, including the mass for a structure like that. What if we shifted the paradigm and that mass came from asteroids and the propellant powering the thrusters, stabilizing it, also came from asteroids? So now this is long term. The theme here is near term, so I'll just briefly touch on the roadmap. So we are first starting with water. We're looking at water for use cases, including propellant. We're looking at carbonaceous asteroids, like what was seen in the Hayabusa 2 and the OSIRIS-REx missions. We believe that the access of these asteroids and getting material from them is the first step. The touch and go or tag phase is what we're currently in. Missions that will be going to near-Earth asteroids, capturing material, bringing it back, finding more about it, turning it into products, and helping to establish the asteroid ISRU value chain that we believe is necessary. Moving forward into ever greater, ever more complex ways to process asteroids to the point where we're actually potentially making those structures. And again, more you can read about on our website. Who are we? Well, we've convinced about 20 engineers to join us in this vision. We're in Broomfield, Colorado. We have people from established space companies, new space companies from outside the space industry, and we're working hard and rescuing thermal chambers from certain death, among other things. So what do we need to do? Well, we have to be great at 3 things. Certainly, we have to be great at excavating or sampling in microgravity. This is no small challenge. We have to be able to get to those asteroids and be able to scale and deploy these missions in deep space. And we have to be able to utilize the resources that we plan to return. And I mentioned scale a number of times. It's hard to overemphasize this. I think people understand scale from the business concept. You have lower unit costs, you can broaden your market opportunities, you can leverage things, you can get more capital. That seems somewhat straightforward, but from an engineering or an R&D standpoint, I think it's often understated how important this is. Think about iteration. We have a number of people from the OSIRIS-REx mission on our team, and if you were to ask them what they would do differently, they have a laundry list of things. That's not because it was a mission failure. Obviously, it was a resounding success. And yet, there's so much that we don't know about these animals. There's so much that we need to learn that there's no way you can do that in just a single mission. Unfortunately, there will not be another OSIRIS-REx mission at a price tag of over $1 billion. We can't afford to look at that. We have to look at a different paradigm here, where we're looking at low cost, more rapid iteration. So that is sort of the driving factor for how we're thinking about things, including the mission that we have that we're working on currently, which we're calling High Frontier. So we've purchased the launch on a SpaceX rideshare in February of 2027. We'll be traversing out to a near-Earth asteroid. We'll take a little bit over a year to get there. We are planning to rendezvous, so this is not a flyby. We are going to characterize the surface, find a good tag location, get to the surface, capture kilogram scale material, and then transmit data of that back to Earth. We are not returning this sample. Celestial mechanics don't allow us a return trip in a short enough time, and we thought proving out this technology was critical for us in order to get more capital and continue more missions. So that we defined merely the ability to get to an asteroid and capture kilograms is sort of the mission objective. This is not a typo. We're doing this for $20 million. That includes launch. Right now, we're holding to that budget with some margin. It's not easy to do, but I'll tell you a little bit about how we're doing that. But that is sort of the critical factor here. So we need to figure out mining technology. Well, this is just some early concepts here, but trying to showcase the fact that we have to think about a variety of factors, including conditions on the asteroid we have no idea about. And so we're iterating quickly. We're looking at carbonaceous asteroids as a source of water, and we're trying to test things in microgravity. That's a very difficult thing to do here on Earth. This is just I don't have a lot of stock videos, unfortunately, but this is not a fluid test bed, this is sort of multimedia. We have some Orbeez, they're these little gel-like materials that can help us with buoyancy, so we're looking at granular dynamics and cohesion forces here. Now, this doesn't represent an asteroid, of course, but we're able to bend the laws of physics, or at least how they behave here in a test scenario a little bit, so that we can actually try to capture that in a simulation where we can tweak things a little bit further. So there's sort of an interplay with physical testing and a simulation that will allow us to think a little bit more creatively here. But as you can imagine, there's so much we don't know that the ability to take some risks is pretty key for us, hence the ability to move quickly and cheaply. So we have to get out to the asteroid. This is an early concept of the spacecraft we're developing. It'll clock in around 620 kilograms. We are designing most of this ourselves. That wasn't initially the outset, but for many reasons, we decided that we had to actually do that in order to move quickly and keep some more control over the process. A few things we're not developing, including the thrusters, but most of the items, including everything that I've bulleted here, we are building. And I often get asked, what keeps you up at night? Depending on when you ask, it's usually one of these things that we're working on. But we were planning to fit into a rideshare XL plate. Yeah, we're targeting the unit cost of this under $10 million. And that's the only reason we're able to continue to do this at the rate we would like to. This will be powered by 3 ion thrusters, Hall effect thrusters. We're using xenon as the propellant. At least for the initial phases of our business, for the first few missions, we think electric propulsion is really the way to go for deep space. High efficiency, but it certainly is low thrust, which adds some challenges, as we'll find out in a moment. We need a decent amount of power. 5.5 kilowatts is a lot for a small spacecraft. That's a lot for a large spacecraft. If you know anything about these numbers, they probably should pop out at you because we have to design this array ourselves in order to get the power and the lightweight that we need. If we fly with this, with the numbers we have here, which we're confident we'll get to, that'll be the highest packing density flown in space. Not because we want to, because we need to with the forcing constraint of our budget and our time frame. The guy who's designing this had this idea for years. Couldn't get anybody to take it because they were happy with what they had. It was sufficient. So in our forced case, this innovation will have the light of day, so to speak. So it's one example where we're trying to do some things creatively. I'll pass through that just because time-wise, but it's a rendering of how we might approach the asteroid. In addition to hardware, we're looking at optical navigation and an ability to autonomously fly our vehicle, capturing at any point in time, our orientation in space, being able to make trajectory course maneuvers as we go. We'll do some radiometric tracking in this first mission on a weekly basis just to calibrate things, but ideally this is run autonomously. A lot more I could talk about that, but in the interest of time, I'm a recovering data scientist, so I've been mostly involved in this. Unlike engineers who speak with numbers, I find numbers too limiting. The world is distributions, don't you know? So we're looking at not just the target that we've determined, but a range of possible targets. And that allows us to form a mission profile where if we have to make some adjustments, including perhaps the spacecraft gets a little heavier, we have less prop, therefore less delta V, there may be an ideal target that falls out of range. We have to go to one that's less ideal. Well, that's a trade we can make. And as we're iterating in our design process, we're able to do that. And that also allows us to generalize for future missions with other asteroids that we may reach with the similar spacecraft and mission architecture. I don't know if this video, yep, there we go. Okay, I mentioned earlier solar electric propulsion and that we're getting a rideshare to low Earth orbit. That means we have to get from low Earth orbit to heliocentric orbit under our own power. We're doing so in a spiral out maneuver that is fairly complex and has never been done before. Also something that keeps me up at night. Not because it's fun, because we have to, but this will force us to figure out a number of challenges as we do this for several months, passing the baton from one communication network to another, sorting out radiation exposure and all kinds of things. We're not bringing any material back this time, so we don't need to worry about processing it yet, but we will be in future missions. This is a very simple rendering of the fact that in our next mission, we will be trying to extract water in situ, and we will be looking at probably a water-based reaction control system, but potentially you could use electrolysis and decompose it into oxygen and propellant that we'll talk about more here this week, I'm sure. But that is one of the aims here. And this kind of brings me to sort of what I want to end on here, which is we're doing a number of things, building the spacecraft, designing the mission, looking at developing propellant from water, and maybe evolving beyond that. But there's so much more that we can be looking at. We're going to be bringing back regolith. We want people to look at this regolith. We would love research in academics and industry to be looking at how we can use the product that we're bringing back from these asteroids. If we're starting to be able to do that sustainably. I'll speak frankly, I'm not super happy with the way that the discourse is happening in the country that I currently come from. I don't think that's the way to win the day here. I don't think nationalism and entrenching ourselves in that way is going to get to the cooperation we need. And so when I think about collaboration here, I think about how we can do things together. I think the global resources that we're talking about will come from a combined community of people. So we're making simulant, which is artificial material. We're looking to distribute it. We'll sell it to anybody that wants to buy this and participate in research. We believe that if you have an idea that could be useful for asteroid regolith, additive manufacturing feedstock may be one example, we'd like to work with you. So this is my call to action, because I think collaboration by doing really is the way to go. And I'm constantly inspired by the scientific community and the research that happens. We need to do this for our own design purposes, but we really want to build an ecosystem that will bring about the regolith age. So let me know if this is something you're interested in working with, if you have some ideas, if you want some simulant. I couldn't bring some because we're not able to figure out how to get it through airport security yet, but it is really interesting stuff that we're building. So Daynan Crull, that's my email there. Let me know if that's something you're interested in following up on. This is just a handful of the amazing team that I'm working with that makes this all possible. I don't know if I have time for questions, but thank you for your time.
Thank you, Daynan. We don't have time for questions because we have to get going towards lunchtime, but thank you, and I know you're on a panel later. Thank you. So our next speaker is Tobias Flecht from Lunar Outpost and is going to talk about, you're going to do the baton handover of a microphone. So Tobias Flecht from Lunar Outpost, developments at Lunar Outpost on surface mobility and lunar night survival. Thank you.
Good morning, everyone. Thank you for the nice introduction. I'm working for Lunar Outpost, which is a global company operating from the US, from Australia, as well as from Luxembourg. We're around 120 people globally, and what we're working on mainly is two things: lunar mobility and lunar night survivability. Let's cover the mobility first. So we're most known for our rovers. And you might have heard that in March, our first rover reached the lunar surface. After that, we are going to launch 2 more rovers next year for different customers also. And after that, we have another mission scheduled for the Australian Space Agency. Beyond the robotic mobility, we are also offering mobility for astronauts. We're working under a NASA contract on the next generation of the Lunar Terrain Vehicle, where we have teamed up with a great consortium. And the goal is to provide mobility to the Artemis crews, as well as unmanned, autonomously operating for a wide set of payloads. Vehicles are important for mobility, but there's a second part, which is also important, which is understanding the environment. And therefore, we have teamed up with another consortia to build a LiDAR satellite. We're doing this by answering an ESA call for small missions to the moon, and we hope to de-risk future surface missions with that, as well as support mission planning on the surface, which is probably relevant for everyone in this room. So, as mentioned, we had the first mission at the beginning of the year. The Lunar Voyage 1 was the first commercial rover to reach the lunar surface. And this was really important for us because it allows us to increase the TRL of key subsystems of our rover. Additionally, this mission demonstrated resilience of our rover because it survived an off-nominal landing and operated after that for several hours autonomously. We were able to collect data from the moon, receive telemetry, and most importantly, the rover was prepared to dive. Several subsystems, including thermal, were operating, and also our mission control center exceeded the requirements regarding uptime beyond all expectations. Our second field we're working in is power. And our rovers have to survive in a very, very difficult environment, from a thermal perspective as well as from a power perspective. All of you have seen, probably have seen this picture in one way or the other in the past. It's showing the temperature distribution on the lunar surface. As you know, the temperature at the subsolar points can reach temperatures up to 120 degrees, and on the night side down to minus 200, and even colder locally, close to the poles, or at some geological features. Also, power generation is difficult because we have a night of 14 days, and using solar electric power systems is therefore very unfavorable. Different entities are working, doing research on different technologies to tackle this challenge. And those technologies can be grouped into 4 categories. One being heat generation, where you use electrical or chemical systems to generate heat. You can use energy storage, which includes, for example, fuel cells or batteries to store heat for the night. Or you can use variable heat rejection to make your system lose less power energy during the night. Or you simply extend the temperature ranges your system can withstand. In my personal opinion, it's not possible to use only one of them. There's no silver bullet solution. Instead, you would need a combination of those. And we have built one of those combinations. The Lux thermal system was developed under a Lux Impulse contract of the Luxembourg Space Agency and is technically supported by the European Space Agency. It's a stationary system which is foreseen to autonomously provide heat as well as power and shelter to mobile systems on the moon, but also to stationary systems in the proximity. How does it work? What we're doing is we collect solar energy during the day. We have 14 Earth days of lunar day, during which we can collect solar energy. We route this power into an energy storage system with a capacity of up to or more than 40,000 kilowatt hours. This energy is then routed during the night to different locations. In a controlled manner, we can use it, first of all, to heat up a thermal garage within the system, which provides shelter to smaller rovers, which are able to enter the system during the night to be in a safe environment. Secondly, we can route the power to the outside of the system and therefore provide heat to customers in proximity, like larger vehicles, think about our LTV, or stationary systems like your ISIU plants, for example. There's a third way to distribute the heat here, which is into a thermal to electrical conversion system. Here we use the heat to generate electricity, which is then also provided to customers, either on the inside or the outside of the system. We can generate up to 100 watts of heat, which we can provide to customers, or 50 and/or 55 watts of electrical power, which can also be provided to the customers. The thermal garage, as we call it, which provides shelter to the customers, is kept at temperatures above minus 20 degrees, which most electronics can withstand. How did we get there? This was our development roadmap. We started with developing key subsystems. We identified early that controlling the heat flow is actually the key in here. So the development started from an active thermal switch, which can withstand very high temperatures, but is at the same time able to route high power. This switch is actually flying on our rovers. It was early prototype was on our first rover mission, and the second early version is on the next mission we are flying. From this subsystem, we went to a scaled-down demonstrator where we wanted to test the key functionalities like collecting the heat, storing the heat, distributing the heat. The testing of this scaled-down demonstrator concluded last year, and now we're working on a bigger prototype, the Lux Thermal Earth prototype. This one is now doing the full chain, end-to-end, collecting heat, storing heat, converting the heat into electricity, and then also distributing it to the customers. This system is full scale. We have a mock-up standing in the hall, if you want to see it. And the goal of this prototype is to increase the TRL of several subsystems. Based on that, in the next development step, we want to finish the final system, which is Lux Thermal. That will be the spaceflight system, which will hopefully be deployed on the moon. Why are we doing this? Because we want to keep this guy alive for more than 14 days, but in the best case, for more than years. Because he's carrying potentially your payloads, and being able to operate them for longer periods is crucial for such missions. Before I get to the questions, I would like to introduce some people here, because, of course, this is not being built by a single thermal engineer. We have a big team, 15 people are working here in Europe, and some of them are here today, and I would like to invite them to stand up so you can identify them. Lunar Outpost personnel. Yes, I can see Olufemi, our electrical engineer over there. Unfortunately, I'm a bit blinded by the lights, so I cannot point at other people. But if you see someone standing around you, please feel free to approach them after this presentation. As mentioned, this project is funded by the Luxembourg Space Agency and supported by ESA. Thank you for that, much appreciated, and thank you very much for listening.
Thank you. Thank you very much. Actually, we're not going to take questions because we've had a very long morning session, so you know who you need to talk to. You can jump on them at lunchtime. Next up, we have Will Coogan from High Frontier Firefly Space, and he's going to talk about Firefly's Blue Ghost Mission 1.
Okay, thank you, Lisa. So yes, I'm Will. I'm Chief Engineer for the Blue Ghost Mission 1 lander. It's a very exciting year for Firefly to be represented at Space Resources. For the first time, a commercial company has demonstrated that you can land softly and operate on the moon and operate through a full lunar day, achieve all payload success criteria, and beyond that operate into the first part of the lunar night. So it's a very successful mission. That's not actually what I'm here to talk to you about today. You all are interested in operating on the moon for the most part. So I'm going to tell you about some of the things that went wrong. Some of the things that, anytime you're operating on a new planetary body, you learn new things. Some things are unexpected, things that will inform your future operations. Quick overview on Firefly. We make rockets, we make landers, we make orbiters. We're able to achieve all this with a relatively small team, partly because we share a lot of technologies between our various products, but also because we are highly vertically integrated. To date, we've laid up several football fields worth of composites. We've performed more than 1,000 hot fire tests of our various engines. We make all of our core avionics for the lander and for the rocket, and do many other things beyond that. Blue Ghost Mission 1, its primary objective was to fly 10 NASA-sponsored payloads to the surface of the moon and operate them through one lunar day. These are performing science demonstrations, they're performing technology demonstrations, really just paving the way for the Artemis missions and helping us learn more about the moon. I'm going to start with how we got there. On the left, you will see an image of the lander in the Falcon 9 fairing. It is on top of a dual payload attach fitting. Actually, inside of that is the ispace Mission 2 lander that's presently on the way to the moon. We took a slightly different trajectory than did they. We were launched almost all the way out to the moon. ispace kept on going past the moon. We did 3.5 orbits around the Earth. That is not as long a trajectory as they took, but still longer than others. It's very important to us to make sure that all of our lander operations are proven out before we get into critical operations. All of our engines are calibrated. You can see every time that plot there changes color, we've done a maneuver. It turns out actually our very first maneuver was accurate to within, I think, 2 millimeters per second of delta V. So that system was all operating very well from the get-go. But it also gives us a chance to troubleshoot some of our payload operations. Some of these are operating in space for the first time. They're really figuring out how to operate in that environment. And you don't want to be troubleshooting when you only have 2 weeks to operate on the surface of the moon. So this gave us an opportunity to prove out those operations, get everything working nominally before we go into critical maneuvers. After lunar orbit insertion, the main remaining activity is to prove out our vision navigation system. On the top there, you can see real imagery gathered from our vision navigation camera. Below is what was rendered on board the vehicle. We are looking through our cameras, and at the same time, we are rendering what we expect to see through that camera based on the seat of our position and on our attitude. And if those two things are different, then we can correct and figure out where we actually are and what way we're actually facing. So you can see that system performed extremely well. Onboard software, creating images that looked almost identical to what the cameras were actually seeing. You could maybe see on the horizon there, there's a little bit of pixelation, but otherwise very spot-on rendering. Okay, and here I actually want to spend a little bit more time talking through the final moments of descent, because this does play a large part in the operations on the lunar surface. Here are 4 different cameras imaging just from pitch over through the final part of vertical descent onto the lunar surface. Now, I don't think we've shown some of these videos publicly before. Top left is looking north and down the side of the vehicle. Below that is looking south, down that side of the vehicle. Top right, we are looking, that's actually the Earth. in the field of view there. It's just a little oversaturated, so we are looking west. And then bottom right, we are looking east as the rising sun. It's about 3 to 4 degrees over the horizon, so very similar to what you would see on a polar mission. Here we are landing at a mid-latitude. I mentioned some things were unexpected. We have pretty good thermal models for lunar orbit, but still things are a little hotter than we expected, enough so that you can see some triangles under antenna on the top right on the deck where the silver Teflon tape is starting to peel up a little bit. It was a little warmer than expected for that adhesive. On the bottom left, you can also see something flapping. That's not in the wind, as some people have suggested. We're actually pulsing our engines 4 times per second. That's vibrating the radiator panel, and it caused our radiator cover to open. It's important to cover your radiators during transit because you're basically just throwing away power from heat that entire time. But it's also important for landing because, as you'll see, as we start to get some plume surface interactions, you'll see them starting shortly, you start to generate a whole bunch of dust. Everyone here, I think, knows the types of problems you can get from dust, but it essentially makes your radiators start to act like a heater when the sun is shining on it. And even micron thickness levels of dust can cause that to happen. So now you're seeing some of those plume surface interactions. You're seeing some of that dust get kicked up. And as we get closer, you'll see this is actually it's a very more of a violent event than you might expect for how soft a landing this was. And you can see that radiator cover is just really getting pummeled with regolith, and that radiator itself was also covered with quite a bit of dust. And here you can see just a different camera point of view, the silhouette of the vehicle. And for all the dust getting kicked up, you can see this is a very gentle landing. It came straight down, threw some rocks into the horizon, but what was otherwise a very gentle event. We've got one more vantage point taken by some of our payloads here for the final moments of descent, looking under the vehicle, so you can see what's happening. And this will also show the effect that it has on the lenses of the cameras. So our main engine is off. You can see the main engine in the top left. We are coming down just on our pulsed RCS engines. They're small 200 Newton engines, but we're firing rockets right at the lunar regolith. So as you might expect, it's a somewhat violent event. And now you can see that some of the lenses are actually completely covered in dust. So how do you clear that dust off of surfaces? We unintentionally discovered one such way. Here you will see a fifth leg we developed to deploy a payload to the surface. You'll see a light turn on, and then you'll see this lens get cleaned. And just like that, it is clean. That payload is flowing nitrogen out of it as a way of collecting samples. That's developed by Honeybee Robotics, pictured there in our Mission Operations Center. And so we discovered that is one way that you can get dust off of surfaces, and we did, in fact, use that to clear some of the dust off of our radiators with our attitude control system. I'm going to actually skip through some of the payload operations just for the sake of time and get into the lessons learned. But at the end of the mission, we got through payload operations for all 10 of our payloads and got them the data that they were after. Just by coincidence, we also happen to be on the surface during a solar eclipse. Solar eclipse on the moon can last up to 5 hours in complete darkness. During that period of time, you hit both lunar extremes. It was just after lunar noon, so it's more than 100 centigrade on the surface, goes to about minus 200 centigrade over a very short period of time. We're able to prove that our electronics were able to operate through that as long as we gave them sufficient heater power. And then we went into the sunset really just kind of guns blazing, all payloads operating, our high gain array operating, all the cameras operating, and gathered data for as long as we could for really our highest power mode of operation. And there you can see the crescent Earth just above the antenna there. Okay, so on to lessons learned here. For as successful a mission as that was, we had almost 60 in-flight anomalies. These include things, though, like the peeling tape. It wasn't anything that was mission-threatening. If I didn't have the imagery, I wouldn't have even known that happened. But it was something that was not exactly as planned, and therefore it is an anomaly. Some did not really have a deleterious effect, like our landing velocity. In some ways, it was too soft of a landing. But you could probably see just from all of that dust flow underneath, there was a little bit of an air cushion from the engine exhaust that arrested our rate of descent when we had intended for it to be constant, and that meant we hovered over the lunar surface for a little bit before we made contact. So this is something that also caused the vehicle to tip a little bit. You might have seen at the end of the video, the lander settles down to roughly level. That is because the surface under the vehicle is not perfectly flat, which means that air cushion is not perfectly distributed, which could potentially cause the vehicle to tip over. But the main thing we found was the thermal environment was more extreme than we expected. We had intended to have the radiators covered, but obviously that dust gets into everything with so much interaction between the plume and the surface. But in addition to that, there was a crater nearby us, and it was really the combination of the dust and that crater near us that was reflecting heat back at the vehicle that made some of the components get 10 to 18 C hotter than predicted. So there's a lot of stress on lunar night survival, but lunar noon survival is also no joke. And that's something that I think had not been observed before on the surface of the moon. We were able to get through it. The team came up with a number of different mitigations, some of which are listed here. So we were able to operate throughout that entire period and ultimately make the mission successful. And then I just wanted to shout out that we do have 2 more missions on the books. We've got one going next year to the far side of the moon, and then one the year after. Both of those are bringing orbiters with them so that we can operate on the far side of the moon as well as at the poles where there's no direct line of sight to Earth. And I don't believe that we have time for questions, but please feel free to find me during the lunch hour. I'm happy to chat with you then.
Well, actually, I have been given the go-ahead to allow 2 minutes for questions. So that means we can have one question, perhaps. So very quick, 1 or 2 questions from the room, possibly. Oh.
People are hungry.
Oh, we have one question, sorry. Yeah, and they're hungry, but we do have a question. Thank you.
Sorry, you showed an image of the sunset, and as the sun was setting, you could see this kind of cloud around it. Is that an optical effect, or is that dust scattering? And if it's dust scattering, that would be super interesting to investigate a bit more. Yeah,
so one of the reasons NASA asked us to image the horizon is because there was an astronaut who observed an effect where we think dust is levitating on the lunar surface as the solar wind goes parallel to the lunar surface. So right at sunset, it's expected to levitate, and because the sun's coming through that kind of scant atmosphere, we should be able to see it. We did see a glow, but I'm not a lunar scientist. I don't know if that was dust levitating or if it's just the corona of the sun extending, way beyond the disk of the sun. But I can tell you we were in total darkness for a period of about 4 hours. Those cameras were very highly exposed. I think those were 4 or 5 second exposures to get those sequences where you see that glow. So we observe a glow. I can't tell you for certain what is for or what it's from, but NASA they have those data and are investigating.
Well, thanks. I mean, just for context, so people in general are super concerned all the time about levitating dust getting on everything. But there's very little evidence to suggest what happens for and against. So this could be a really interesting result that you've got there and worth looking into.
It could be, and NASA's looking into it.
Thank you for the question and the observation too. Any other questions? Okay, we'll move on. One talk between us and lunch, but thank you very much indeed for the lovely images. Thank you. Beautiful images. And now we'll move on to the exploration company, and we've got Pierre Faucoup. Pierre Faucoup, thank you very much.
Good morning. Good morning to everybody, and thank you, Lisa, for the introduction, and thank you for inviting me to present where we are in the exploration company on the road to the moon. First, I would like to make an introduction by reminding where we are as the exploration company at large. So we have been created 4 years ago, roughly. We born in France and Germany at the same time and at the same level people. And we are now based also in Italy, in Turin, and in the US, where we are developing our activity in relationship with different potential US customers. And more will come sooner, but I can't say more now, but we'll plan to open other subsidiaries very soon. Because we are considering us as a really European company with European roots, but we have the ambition to be a global actor in space. Today we are more than 270 people. We plan to be more than 300 before the end of this year. So we are the fastest growing startup in space in Europe. We have signed more than 800 million euros of contracts. Main contracts has been signed for LEO destination, with the commercial space stations, but also with the different space agencies in Europe, mainly with ESA, CNES, and DLR, our, I could say, mother countries. And in addition to these contracts, we have raised more than 225 million euros with different steps, and with the last one was 150 million euros fundraised for the Series B at the end of last year. So what are we doing? We are developing space vehicles with two destinations. First one, the LEO destinations, with a product which is called Nixus. You can see on this picture on the right. And we plan to reuse as much as possible what we are designing for Nixus to go to the moon. And we are really working with this objective in mind to reach moon as soon as possible. So first, I would like to present you where we are on the LEO destination. We have decided to go to the Nixus full-scale vehicle by two steps. First steps is demonstration, which has been called Bikini. Bikini has been developed in 9 months in 2022. As you can see, different steps on this picture. After that, we waited for the launcher because we were on board the Ariane 6 maiden flight, which was a little bit delayed. So we take advantage of this time to make additional tests on ground, to learn more, and to be sure that our demonstrator will do its objective, which is mainly to qualify, not to qualify, but to have a better understanding on what will be the re-entry phase, which is a very critical phase of the mission. You can see the different steps of integration of Bikini, even on the launcher, and on the left side, you see Bikini on board the last stage of the launcher of Ariane 6 in flight, in space. And unfortunately, there was the last part of the mission of Ariane 6, even if Ariane 6 is a big success for Europe, the last step was not performed, and we are still flying on board this Ariane 6 in space, and it was not possible to be launched, to be desorbited with them. The next steps the next demonstration step is called Mission Possible. Mission Possible is a capsule of 1.5 meters of diameter. You can see also on this slide the different steps which has been performed between the first design in July 2022 and the environmental test which has been performed in Airbus facilities in Toulouse in last summer. This Mission Possible has the particularity to have customer on board, and we can see on the circle tube different experiments we have on board. We are very proud to have both institutional customers like ESA, CNES, and DLR, or also commercial customers. Again, you see the different steps of integration of the capsule with, on the left, the final steps, which is the departure of capsule from our integration site in Munich to fly to US for a preparation of a launch, and will be launched on Falcon 9 in the coming weeks. Can give a more precise indication, but for sure, if we are already there in US, that means that it will be soon. This demonstration will be a 3 hours demonstration in microgravity environment. After that, we will re-enter on Earth. We will splash down in the ocean close to Alaska, and we will recover our capsule to, of course, first recover it and to give the experiments to our customers. These two steps are preparing the most important for us, which is the Nixers flight. Nixers is a full-scale capsule, which will dock to the ISS. On this project, we are supported by ESA, who is our anchor customer. So we'll participating to a competition which was made last year by ESA to provide cargo services to ISS. You see on this slide again the different steps of development with important steps which are also the different safety reviews which has to be performed with NASA to have the certification to dock to the ISS. Concerning Nix Moon, we are thinking about two types of configuration. Either Nix Moon as a docking vehicle with, as I mentioned, important reuse of different elements of Nixers, and also as a landing hopper by reusing the service module. Of course, we have in addition with other specificities. So, for example, on Nix Moon docking, we imagine that this cargo could deliver things to the gateway, to the lunar gateway, and after that to re-entry back to Earth. To give you a more precise information, what I say that we'll reuse as a maximum what we are designing for Nixers. For example, for Nixers, we have chosen thermal protection material which has been already qualified to be able to support the re-entry from the moon orbit. That means that we are not we are designing directly with a material which is able to perform the two types of missions. The other mission is the landing and the hopper. So with by reusing the service module of Nixers. And in addition, of course, we'll add a cryogenic propulsion system. In the exploration company, we have decided to develop and to produce our own products and the critical functions of the vehicle. Of course, the engine are part of these critical elements. So that's why we are already developing our cryogenic propulsion for the Nix Moon, which this engine is called Huracan, and you can see one test which has been performed in the DLR installations in Germany. So we have a roadmap where, in parallel of the development of Nix Earth, we are already developing the engine with this schedule. So to have the engine ready for qualification in 2028, beginning 2028, we are supporting by ESA for this development. And in parallel, we are also working on a demonstrator on the hopper demonstration make on ground, and we are in intense discussions with different agencies to be supported in this initiative. And with a final goal to provide a first Nix Moon mission in 2029 or 2030. So that's our roadmap, where we are reusing as much as possible what we are developing for Nix Earth, but we still have in mind that our main objective after is to reach the moon and to be part of the moon economy. Thank you for your attention, and as I am a final one, I think we are going to lunch now. But ready to answer your question, of course.
You are quite right, Pierre. You're quite right indeed. We're going to lunch. I'm not going to allow any questions because we're bang on time, 12:30. Thank you, Pierre. Thank you very much indeed. And yes, it's lunch and we will be back in here for 1:30 to start again. Thank you.